All right, thank you. So, thank you so much to Yanbin for being here today. It's a pleasure to welcome him. I consider him a brother because we both had the same PhD advisor, Matt Mason, at Carnegie Mellon, where we overlapped for only about a year or so. I was on my way out, he was coming in. And Yanbin did his undergraduate degree in China, and he did a very prestigious special degree there at the very well-known University of Science and Technology. And he then spent a little time doing temporal logic at the Chinese Academy of Sciences. And he's moved on from then. He came to Carnegie Mellon as doing work with Matt Mason, and hopefully he's going to mention a little bit of his work there. He did a lot of work on geometry, studying of grasping. He's done work on tactile sensing. He spent some time at the University of Minnesota. He was a professor there. He also has done visiting stints at Stanford and at Carnegie Mellon. He's also had a very illustrious career being a very engaged with the IEEE and with the National Science Foundation. He's had a number of grants. He's been on a number of important committees, including associate editor of the Transactions on Automation, Science, and Engineering. And he has been on the conference editorial board and created a special issue of IJRR. He's won an NSF Career Award. And his lab is pursuing a number of different topics. Most recently, he's got a very interesting new passion for studying deformable objects and grasping and cutting of deformable objects, which is particularly interesting to my own group, and I hope to many of you here. He's been looking at impact and some of the potential of how things are being, how to model deformations in this way. So please welcome Yanbin for our series. Thank you. Yanbin?
Yep. Thanks, Ken, for inviting me. I feel honored to be able to present our work in Berkeley. And Ken has been a tremendous source of support and appreciation over years, ever since I was a graduate student. I'd like to actually correct Ken a little bit. I did PhD in the lab directed by Matt, but my advisor was actually Mike Erdman. So it was a little bit confusing because I work with Matt indirectly as well. And Ken and I, we barely overlapped. We just narrowly missed. I think Ken finished in 1990 and entered the CMU in 1990. I always look up to Ken and for the research he's done. And I'm grateful to him for being an enthusiastic advocate of our research. I wish our students are as productive in research, as strong in problem solving as graduate students at Berkeley. So I'll start. Okay, if you allow me. So today I'm going to talk about, okay, I'm going to talk about two tasks mainly, which require some sophisticated manipulation skills. So what does such kind of robotic maneuver require? It requires modeling, understanding the mechanics and geometry of the task, requires the algorithm. You know, Ken used to be a leading expert and he still is on algorithmic robotics. So I still have a fever for that. And then it has optimization as well, you know, so optimize energy, optimize time, for instance. But when it comes to execution though, especially for contact-based tasks, you have to go through control, you know, to exhibit this kind of a, you know, compliance, you know, whether it's position, force, impedance control. And also there's got to be a good state estimator, either using computer vision or common filter. So today I'm going to look at batting and cutting. And also there's a derivative task I like to look at and derive from the batting, which is on the motion estimation. All right. So this is the batting. This is the work done with former student Matthew Gardner, who's currently working at Boston Dynamics in the Mountain View office, and the current PhD student Xiao Qian. So we picked this task because we think this is a very highly skillful move, even for a human being who has difficulties. and it challenges both sensing and action. But when you decompose this, though, you see there are so many ingredients there. There's impact dynamics, there's a projectile mechanics, and then there's kinematics, vision, and state estimation, and also not to mention planning. And it has some very interesting applications, especially to robots in ball sports. It goes through, whether volleyball, soccer, or through impact, right? Or ping pong. So this is a system architecture. When you look at this, though, if you focus on the left side, so there's an object flying towards a robotic arm, and then there's a camera, a high-speed camera, and 150 frames per second, capturing these images and sending it to the image processing, triggers the state estimation, which get the velocity and the angular velocity currently, and then the planner will, in the meantime, just anticipate in a certain time instant the bat, which is fixed on the robotic arm, to meet the object and bat it, okay? And also the trajectory, the rebound trajectory will have to get to a target, okay? So the state estimation results in, at a particular time instance, the pre-impact velocity and the angular velocity, and then the arm is moving as well because it's very fast. It's only like 7/10 or 6/10 per second, and then it has to meet at that point, and then there's the impact will predict the rebounding, velocity and the angular velocity, and then at that point now it's all open loop. Okay, so the object has to fly, and then we're using projectile mechanics to characterize the lift forces, and then the Magnus forces, and then the drag forces. And then it has to go through that target. So that's basically use it as a constraint, which is employed by the planner to generate the pre-impact, at that particular time instant, the pre-impact joint angles and joint velocities of the arm. Okay, and the arm is moving right away, and then the better state estimates are obtained, and then it's making dynamic and making these adjustments. Okay, so there's a lot of work. I think since we're running out of time, I just like to skim through it. There's a great work by Newton, Poisson, so there's the kinematic restitution, kinetic restitution, energetic restitution, which is the only one that's consistent with energy conservation. There's work done by Dabu, Roos, and Ken's PhD advisor, Matt Mason, and Yu-Wan, former student. And then there's also Berkeley colleague, Kenny, and former student, Murtik. And then there's the impulsive manipulation, where they're using, electromagnetic forces, using Airtable to orient objects, and doing batting and tapping, orienting as well. And recently there's the interest in the catching flying objects. But then there's also some work on batting, except they only interested in bat the object regardless of where it goes after the impact. And in the table tennis, from the Anderson's first robot playing table tennis to Dr. Sheng and Zhejiang University's robots, 2 humanoid robots that holds the record of rally that has over 170 shots. Okay. So the thing to solve this impact, so we started with 2D, okay, and then so the object's flying in the plane is this equation. When you look at the contact velocity, its change is actually represented as the product of the inverse inertial matrix with the impulse. So you basically let the impulse accumulate, and then you look at the end of the impact, what the impulse is, so you can calculate the post-impact velocities of the object and angular velocity of the object, okay, from the pre-impact one. So of course, the issue is how to determine the total impulse. Okay, so we have the impulse that's in the normal direction, tangential direction, and then we also have the contact velocity decomposed along the tangential and normal directions. So we do this case-by-case analysis, like what Matt Mason and Yu-Wan did, and then look at the several critical moments where the compression ends and restitution ends, and also when the tangential contact velocity becomes 0. So what we did differently is we use energetic restitution. We track the energy. So the compression ends when the normal contact velocity becomes 0, but restitution ends when all the energies gets released and converted back, or dissipated after some dissipation, converted back to kinetic energy. Okay. So then there are 3 contact modes. There's stick, slip, and reverse slip. And so here the variable has only one variable, which is a normal impulse. and the tangential impulse is a function of this variable. Okay, so you just let this impulse accumulate, and then you check this critical moment, and then in the meantime, you track the energy. So there's the impulse in the center and the contact velocity and then the energy, okay? And then the energy is varying, and then the relationship, the impulse changes the dynamics of the objects that are in impact, changes the contact velocity, and under Coulomb's law, and there's different contact modes which will govern, in turn govern the change in the impulse. So the questions that haven't been answered and have not been answered in the history of the impact is, okay, people say that we have, this restitution, then we have Coulomb's law, are they consistent? Will, the compression end? And the second, will restitution end? So we give a proof that the impact process as modeled will end. It may not, you can never run into a situation where two objects that are actually penetrating into each other forever. So, all right, so add to that, like I mentioned before, after the impact, okay, the object is in free flight, and then there's air drag, and then there's also Magnus force. So for those of you who play soccer, or you know this banana kick, right? So when the ball is actually rotating, if it has a forward spin, and then it's gonna go down earlier than it's expected. If it has a backward spin, it's gonna travel longer. This is all because the speed of the air on the top and the bottom of the ball are different. So the top is backward spin, and the top, and then it's actually faster, and then the bottom is slower. When it's slower, the air pressure is higher, so that lifts the ball and making it travel longer. So we have these, the drag coefficient and lift coefficient, and we can measure during the experiment. And then the flight now is characterized by the object, post-impact flight, and even the pre-impact flight, even though we're tracking it, is characterized by this ordinary differential equation. And the thing is that we cannot just do the numerical solution because we don't have time for that. The whole thing is just like 0.7 of a second, right? So we basically need a closed form solution. We cannot just solve it because we have to do it many, many times. So what we observed is that we can actually replace the right-hand side with the closed form under gravity only, as if air impedances, the air drags and lifts did not exist. And that actually turned out okay, because if you look at this, now we tested on 3 objects. There's ping pong, there's this dumbbell, with 2 ping pongs connected by a plastic tube. And then there's this fork square. And so now the real trajectory, if you look at the upper right, is this dash trajectory. And then the red curve shows the trajectory that it would follow in a vacuum with no air drag. And that is way off. So when you are planning based on this, it's not gonna hit the target. But if we use our approximate solution that is actually closed form, it generates this green trajectory, which is really close. And the same thing happens with the dumbbell and then the square. So that we've done many experiments and we found that the error is very small, so we trust it. We really want a very efficient way of modeling this. So then there's the flight estimation. I'm gonna basically skim through this because I'm gonna spend a few slides later on talking about flight estimation. So we basically estimate the position and the velocity using extended common filter. And for the orientation and the angular velocity, we decided to do the d square fitting. There's enough speed to keep up with the flight. Okay, so the arm, if you look at the instant of impact though, so there's the contact point, and then that's through the inverse kinematics actually imposes a constraint on these 2 joints. Unfortunately, we have only a WAM arm with 4 degrees of freedom, which can only afford 2 degrees of freedom in a vertical plane, which is the plane of the task. So, and that imposes the constraints, so there's a dependence here. And then what the planner needs to do is to plan the state of the arm right at the time of batting, which includes 2 joint angles and 2 joint velocities. And when you write out these constraints, including the task constraint and the contact constraints and the ranges of joint angles and velocities, and then there's also the impact feasibility, and then there's a realizability, because you give this, can the robot move fast enough to get there, reaching that joint angles and joint velocities, right? So there's a realizability. constraints which are formulated in first order logic formulas that can be tested very quickly. Okay, so there are like 16 constraints, and then these two are equality constraints that allowed us to eliminate two variables. So now here is the planning cycle. So every cycle starts and the acquisition of a new image and then ends in acquisition of the next image. So as soon as an image is acquired, so the arm is already in motion, it has to move right away. And then there's about 3 milliseconds we leave, which is a conservative time. There's enough room for image taking and processing and state estimation and planning, and then sending the command to the robot. So now the trajectory now gets modified, okay, dynamically by the arm right at this point, and then it just goes through until the next cycle. So it just keep updating. All right. So this is a sequence of planned arm states from the 34th to the 94th image frames. And the more and more frames, it has more information, the estimates gets better. And in the later on, just kind of converges in a very small region. So the x-axis is the joint angle of the first joint, and the y-axis the joint velocity of the second joint. Okay, so these are the two variables. We use 2 cameras, and because this is the planner task, we actually printed a big screen and do the calibration. It's in the plane, so we can do it very, very precisely, okay, accurately. And then we use the launcher, a catapult to launch the objects except for the quark. And so now here's the video. Okay, so the first set of experiments is about batting ping pong balls. So we have these squares that are hanging over the ceiling, and then they're randomly positioned. And then for one position, there's only one bat. Okay, it fails, then it fails. Okay, if it succeeds, and succeeds. And the dumbbell thing is more interesting. It's flying, and then there are 3 toy bowling pins, and then the dumbbell is trying to hit that, the batting, after batting. And so this is the miss. This is really hard, and I'll talk about this comparison with performance between the robot and a human subject. So what happens if you put this side to side, the video and the planner, okay? So it's flying, and now into the zoom, into the scope of the camera, okay? And then the arm is moving, and it do some adjustment, minor adjustment of its trajectory, and then trying to meet the dumbbell at the point with the right angular velocity, and then the angle, the joint angle. So the quark one is tough. So we didn't use the catapult, and so Xiao Qian is throwing it, and these 2 are misses, and then the third one was a success. So the success rate is actually not that high, but would be very difficult for a human being as well. This is all in one take. For the ball, it's easy because the aerodynamics is more accurate. We're not doing the full modeling of the aerodynamics. So these are all, now it starts to fail, and it fails again. And then one more bad. Okay. There's another one. Okay, so the final one I'm going to show is we're just batting it towards that cross. So on the floor, there's a big sheet, and then these concentric circles will help us to tell how close it is to the center of the target. So if it's outside the big circle, then it's regarded as a failure. This one is actually very close, and you see that the arm is using slightly different pose. Okay, so if we look at this closely though, so here's one set of 20 batting instances, and these green dots represent the successes. And the green dots with a circle, there are 3 of them corresponds to these 3 instances that are shown here on the left. So the cross is basically shows the vertical distance of the hitting point from the center of the cross, okay, the X. And then so if it's within a certain interval, then we regard it as a success. If it's outside, then it's not. But I think here it's basically the height of the board. So the success rate is very high. So we just use one try. We never try it many times. And one position, one try. It's a 50% success. But for the bowling pin, the success rate is very low. We've done a lot of these trials. It's about 15%. Here's one set. That's 20 of them. This is one of the better sets we have. And there are 5 successes. So basically when it's locked down, and then it's a success for the bowling pins, even if it's one of them, right? And now we asked Xiao Qian to do the same. Xiao Qian didn't go through any practicing. So she was trying to do that. And so we placed these bowling pins, the row of bowling pins at exactly the same locations on the floor. Okay, so this is the x-axis. And she succeeded in 4 of them. And you know that, she actually is doing better. So I think if Xiao Qian keeps doing this, eventually he would have beat the robot and easily, because human learns, right? You practice more and you get better, but ours, we don't have learning in this. Okay, for the net, and so this one, and the success rate is about 21 out of 5. And this is tough. The cork and the dumbbell, they do not, often some of the failures because they do not stay in that plane. They actually swirl out of it a little bit, and then the robot would have a wrong estimation, and the impact, would drive it to a different place and out of that vertical plane, and then so not to mention missing the target. So on this one, Xiao Qian, and compared with the robot again, her performance, so the robot performance is 25 out of 37. So within inside this big circle, that's regarded as success. That's all marked by this red X's. And then these blue dots are the performance by Xiao Qian. You see that she had a bias, she tended to bat it towards the right side. Okay, but the robot actually done better, and obviously better than Xiao Qian on this. So that was Matthew, when she started this PhD, he was working on this batting with me. And then we wanted to do 3 batting, and one of the obstacles we had is to do the motion estimation. So now this is full 3D, and Matthew got attracted to that. Then he ended up spending the remaining 3 years of his PhD working on this problem, and he never had time to come back to 3 batting again. Okay, so we had this object that is flying, and we have 2 cameras. We are going to use epipolar constraints, and some of you may already, I think. And so here is the diagram. So we have 3 blocks, which is the aerodynamics block, and there's constraint common filtering, and that does the estimates, and then there is the feature tracking that is graph-based. So there has been a lot of work from computer vision, but it's mostly not flying motions, and then and slow translation, a lot of these linear velocities. And then you can also use kinematic-based approach by embedding these accelerometers or magnetometers inside the object and using kinematics to calculate the velocity and accelerations by solving equations. Then there's from aerodynamics, aerospace engineering, they use aerodynamics, and then try to model these effects more accurately. So common filtering from the original work by Common, and then extended common filter and unscented common filter, and then their applications to estimation. And then recently there has been some work on using vents for combined vision and common filtering. And for the constrained common filtering currently, to our knowledge, it has only been limited with single constraint. So we've done some work on that. And for feature tracking, there's actually the planar graph matching work by Epstein, which is a polynomial time algorithm. And then when you allow the tolerance and errors, then it becomes NP-hard. So here's how it goes. And that's the aerodynamics part. So we have the lift force and the drag force due to the air. Lift force is due to the friction, of the air with the object surface, flying objects. Okay? And then the drag force is, of course, in the front, and that's the viscous force. And so you get these forces, and then you plug into the Newton's and Euler's equation, and then you update the velocity and angular velocity, and now through the Laplace equation, the velocity, and you generate the velocity potential, and then get a gradient, which will contribute to part of the air velocity surrounding the object. So there's a volume of air surrounding the object where these velocities of these air elements are changing. as the object is flying. And then the angular velocity would contribute to the Magnus effect. So when you plug into the Bernoulli's equation, you get the air pressure. And then when you integrate the air pressure, you get the lift force as well as the torque. And then in the other direction, the velocity itself, and experimentally using closed form approximation, can get the drag forces, which are actually pretty reliable. It depends on the cross section, and that is perpendicular to the velocity direction. So when you look at this, let's say P is a feature. So that's in the body frame that goes to the world frame, and then the camera frame, and then the projection. But then we have these nonlinear effects that need to be modeled finally to get the image points on the screen. So the system observables for us are the point features, and also the epipolar constraints are, which says that the P and its two images, Q and Q prime, and the camera center C and C prime, all 5 points should be coplanar. But of course, there's only nonlinearity. We have to unravel that, and we decided just to incorporate that implicitly by looking at the normals. So the state variables are the object's mass, center of mass, and then the orientation, velocity, angular velocity, camera orientations, and camera's focal points. So there are 27 of them. Now we have the system written out by combining the dynamics with the camera projection. And we constructed extended common filter, the EKF, subject to 3 constraints due to 3 quaternions describing the orientation of the object, the 2 cameras. And the previous work, we've done a survey that we haven't found any work that handles more than 1 constraint. But this is not that difficult. It just requires some algebraic manipulation using the Lagrange multipliers. We can get this equation based on minimizing the posterior covariance. And using the homotopy continuation method, we solve for the Lagrange multipliers, which will lead us to the common gain. So that's updated every cycle. So for the feature tracking part, the object, we have a model. So we just use a polyhedral object, and then so that is represented by a planar graph, and then you have the image graph. The thing is that hypothesis basically sets up the correspondences between these vertices extracted from the image and a portion of the vertices that's in the planar graph. So what happens is that we have multiple hypotheses going on, hypothesizing these different sets of correspondences. Every hypothesis has a common filter and then compete with each other. And we have a way of evaluating them, rejecting them. And when all of them are rejected, we have a way of generating them. So when we do the validations, though, we first thought of, okay, we got to have some ground truths. So this ground truths come from these accelerometers. And it would be nice just to use the XYZ frame as the object and just let it fly. So now here's what happens. Okay, so Xiao Qian is throwing this frame, and this pink one is extracted from the image, and the estimated frame is green. And on the right-hand side, you see the velocities. One is the ground truth that's calculated from solving equations based on the data of accelerometers. And then there's estimated by the common filter. And you see that initially, though, when they have some differences, especially in this x velocity, right? And gradually it just converges. Okay, so that's not enough. Matthew, with Xiao Qian's help, and then work on the rugby ball, and so throw the rugby ball. Now we have to take into account the aerodynamics. So we use reprojection errors to look at how good the performance is. So one is without aerodynamics, and you see this blue curve, and then the black curve is with aerodynamics. So and with aerodynamics, the error is clearly lower, and consistency almost consistently lower. So that means it's important. The reason is that rugby ball is actually light, so the aerodynamics effect is very obvious. And with the frame, though, object, because it's heavy, and aerodynamics effect is negligible. And then Matthew throw this polyhedral object, and on the right-hand side you see these snapshots in particular time. And now you see these feature points, they come and go, some appear and some disappear. So here in the bottom right, and you see these hypotheses that are competing for the first 0.4 of a second. There are 2 hypotheses, and after both are rejected, but at the time, though, when both were alive, we always choose the better one. and the new hypothesis gets set up, and then they are competing with each other, and then the blue one still wins. So there are two hypotheses that actually dominate during in the duration of the flight, and then they give pretty good estimates. All right, now we're down to the last one. I'm rushing a little bit, sorry. Just feel free to stop me. So the last task is actually the second manipulation task is dexterous cutting. And so we want the robots to go into the kitchen to help us. The kitchen skills are the very important part of the home automation. And the robot needs to be able to prepare meals and cut food items, right? But currently, though, in the food sectors, we have lots of these machines for deboning chickens, cutting noodles, and it's one for a specific task, right? So they are not modular. And then if you're going to have all of them in your kitchen, and you're going to have a huge kitchen to have all of these, right? But then where's the skill? But these ones do not require skill because they are kind of designed that way, right? They're machines. They just mind their own business. So we thought, hey, it would be cool if we can have a robot that actually demonstrates some cutting motions that are as natural, as smooth as the motions by human shave, right? So Xiao Qian and Yue Chuan worked on this problem with me. So we still need modeling, and the modeling tool comes from fracture mechanics. And there has been some work from the robotics community on cutting of the biological issues. But these methods are mostly ad hoc. They're not based on mechanics. They're a little bit, but they're not strictly following the mechanics. In part, I guess, because these materials are soft materials. And if you follow mechanics, it gets a lot of this nonlinearity and just couldn't make it a daunting task. And then we need to do the control in order to exhibit those compliant motions. So you go back to the work by Raybert and Craig, the hybrid control, and Hogan's impedance control, and Cut Heap's the operation space. So these are the ones. And then these people now are applying these control measures in cutting. And then recently there has been some interest from the machine learning community to try to apply data-driven approach to learn, the best cutting force and the best cutting trajectory. Okay, so when we look at the cutting though, and we actually decompose it into three phases, and first just escalate the knife downwards until it makes impact. This is a slowed motion. So there's an impact that needs to be softened. This impact is between the knife and the cutting board. And then after, it slows down, and then the knife kind of slices through the object. Okay, so that's the third phase. The second phase is very brief. It's about 1/10 of a second. It's slightly longer than that. But now, if you look at these three phases more closely, though, the contact the knife has experienced is changing. In the pressing, though, it's the contact between the material and both sides of the blade. For this, we can use position control. We can just let the knife translate. Or if we want it to rotate, that's fine. But the touching phase, there's a blade material contact. There's also the knife and board impact. So there's an impulsive force that we need to mitigate. So here, the best control strategy is basically to apply the impedance control in the vertical direction to soften the contact. And in the horizontal, we wanted to stabilize it so we can use position control. And then the last phase of slicing, we wanted to cut the object completely. So we got to make this red dot, which is the contact point, the knife board contact point, to move across the bottom of the object. Okay, so that naturally needs us to hybrid control. We're going to maintain some force on the board. The knife has some force maintained on the board to ensure that the object is cut open as the knife moves through. And then the position control is going to be on the tangential direction to drive these red dots from left side to the right side. So for fracture mechanics, so here's the equation. Basically, this can be understood as the work done by the knife. This is differential. It contributes to fracture. Okay, we use the fracture toughness, which multiplied with the area of fracture. So that's the amount of energy it takes to fracture dA. That's the differential area. And then it also pumps into strain energy. But sometimes the strain energy can be negative, which means that the build-up strain energy actually contributes to fracture. And it may generate kinetic energy, and the knife also needs to overcome the frictional force between the blade and the material. So because it's the beginning of this project, we actually made some assumptions that the knife is moving in the plane of symmetry, which actually makes sense for most of the cutting actions. And then we wanted to focus on the cutting, not stabilization of the object. So we had some fixtures, on the object, so the object stabilized. And then there are plenty of the objects that, that go through negligible deformation during cutting. So the kinetic energy and then the strain energies are both zero, which also gives us a benefit that a cross section is invariant in cutting. Okay, so I'm going to quickly go through this. This is the element of the edge element, and it moves through this area, this parallelogram. So there's a force, that's a cutting force, and we can calculate using the fracture toughness. And then in the meantime, it has the frictional force because it goes through this, right? All of these elements, in this contact area between the blade here, the omega, it has to have friction there, exerts friction force. So the end of the handle of the knife is attached to a robotic arm. It has, here is a force torque sensor, okay? And now if you now put the arm in there, now we have three frames, the word frame, the knife frame, and then the arm frame. And there's joint vectors and orientations of these frames. And then here is where, at A is where the force torque sensor is mounted. It's basically mounted at an open end. So for pressing, it's pretty straightforward. We can just, do the position control and you work out the dynamics of this and just write it in the task space. So when you have the Jacobian of JA of that point A, and then you have all these Coriolis, centrifugal, and the gravity force, as well as the torque and force exerted by the material at the point A. Okay, so these things we can sense, use a sensor there. So what you need to do is basically replace this X double dot with a servo, and then you have a third order, linear time invariant system, and you can choose these things to achieve stability. Okay, so now this is moving fast in the pressing case, and now it's a touching. And so now there's an impulsive force exerted by the board on the knife. And then this is the very brief, and then there's barely any fracture or frictional force. So all measured and here by the force sensor are actually due to this force contact force only. So we use impedance control, and the controller, it looks almost identical to the position controller in the first phase, except here now we're using a desired stiffness and damping, and then the desired mass point for impedance control to exhibit this behavior of impedance behavior. So the third part is slicing, and this is more complicated. It actually involves two Jacobians. I'm not going to talk about that anymore. And the hybrid controller, the objective is to move C, the contact point, from the left end of the bottom segment of the object to the right end. So this is why we make sure that it's cut open. In the meantime, you're going to make sure that it's in contact. So you have to control the normal contact force. All right, so we can prove that the stability of the system as well, although it takes a little bit of effort. All right, so the nice thing about the third phase is that you can actually set the desired trajectory of the C as well as the orientation of the knife to translation, which maps to slicing. And you can also do the rod chop. If you let the knife just roll and you get the rod chop, except this requires the arm to have at least 3 degrees of freedom, which our arm doesn't. In that cutting plane, it has only 2. Okay, and then you can just have a mix of translation and rotation. So we also handle this real-time estimation of the physical parameters. If you look at the 3 phases, though, what constitutes the sensor reading in the pressing? It's the cutting force, the fracture force, and the frictional force. The touching force phase is the impulsive force. And the third slicing force, this is the part that requires modeling because we wanted to regulate the normal contact force on the cutting board while the knife is slicing through the object in order to make sure that it's actually slicing through. So we gotta know the force, the cutting force, and the frictional force. And the thing with the real object is that all the fruits and their values vary with the knife sharpness and the temperature, and with the individuals of the same type or even the freshness, the fracture toughness changes, the friction changes a few days later, after you take it out from the fridge. But we made some assumptions. We actually have a way of dynamically estimating while cutting is going on we can estimate these parameters. So the first experiment was set up. We have these like $200 cheap arm just to fixture the object, and this cannot do torque control, and then it's very inaccurate. And so this WAM arm, the same WAM arm that does the batting, is doing the cutting. And because of lack of degrees of freedom, it has only a unique pass when the knife is in contact. So during the slicing phase. So these are the results. I'm going to show a video a little later. And so the desired trajectories are the dash trajectories. The real trajectories are the solid trajectories. So before the slicing, and we're just looking at the lowest point, C, and we're looking at the Y coordinate after slicing, because now the X coordinate at this point has to move through across the onion, okay? And the contact force during slicing is regulated at 5 Newtons. And then you have the fracture and frictional force that are modeled. One thing is that the modeled forces during slicing is very, very small at the fracture and frictional force. This is actually due to the lack of the freedom, that one degree of freedom that prevents the knife from rolling on the board. And so we had to compensate for these degrees of freedom. So we made a linear guide and just to translate this cutting board and then, and just calculate the right speed of the contact point movement, and just to make the relative contact velocity here as close to 0 as possible, which is shown here. And by doing this, though, we do see a apparent increase in the cutting force and also the frictional force. So this is why we need modeling now. With the 2 degrees of freedom, we can barely do that. So now this cutting force is actually huge. It starts with 30 Newtons. All right, so now this is the video, and then cutting the onion. So it's repeated, that's the setup 1. Okay, and potato. It's getting a little tedious if you keep seeing this, but this is repeated cutting. And if you look at the motion, though, especially focus on the slicing phase, and you see that it's very soft. So the whole cutting action just lasts slightly over 1 second. And then it's actually compliant. It rotates a little bit, right? So this is the one that's the chopping. And then there's a little bit of noise. I'll just turn it down. And so that translating a linear guide just make up for the lack of degree of freedom, and just makes the whole action looks like slicing. I'd like to mention that the older version of this video was actually featured on March 31st, 2019 in IEEE Spectrum News on Robotics. So there's some future directions for 3D batting. The computation is a big issue, and we can actually also work on the compliance, because to let the ball stay with the bat longer with the object. That's actually what happened in, with tennis and soccer. So there's a more tangential impulse that can change your trajectory more dramatically. And then the estimation and planning can be a big hurdle. And Matthew was only able to do the estimation, but it's still not a real time. For the dexterous cutting, and definitely, one of my students and we have been working on modeling of different deformable cutting. And then there's also the work optimization, minimization, and the pass planning, just make it effortless. How do you characterize? Maybe the energy expense of the knife, or energy expense of the robot. And then there's coordination between the cutting hands and the holding hands. How do they talk to each other? To communicate through force interactions. And then we can actually also look forward to composing multiple cutting skills, the basic cutting skills, and chopping and slicing, maybe to do more complicated ones such as dicing. So I like to end this talk with an acknowledgement of the 2 of the grants that funded the research that's presented here. So I'd like to, I'm happy to answer any questions you might have.
Excellent. Thank you, Yanbin. 2 great project, and very interesting that they're very especially the cutting is something that I've never seen before. I think everyone has questions, but if you don't mind, I'll jump in. And the first one has to do with the 2D plane for the batting, because so curious because as you said, the degrees of freedom of the arm are limited. It's a 4 degree of freedom arm. So how do you launch the pitch, if you will, to the bat? And what is that process? You mentioned it, but it went by kind of quickly.
You mean the batting one for the
Mm-hmm.
bat, right? Yeah, yeah. So as soon as the object takes off, and then the arm starts moving, and so it has an anticipated time of collision, the bat colliding with the object. So it plans according to that. But as the frames of images coming in, it gets better estimate. It just modifies. So we use like a polynomial. This is a good question. And we use polynomial interpolation. Use the Craig stuff just to change it.
So what I'm wondering is, though, I mean, I presume it's at least for the ball, the spheres, it's it's a ballistic motion. But how is it being launched? I mean, because that you mentioned about the spin. I mean, you could imagine it could be spun, but I presume it's not. So how do you launch?
Oh yeah, that's great. So there's a catapult. We use a catapult for launching.
Okay.
Yeah, and it's not that we want it to be repeatable. We actually don't want it to be repeatable, but we just wanted to have the catapult so it actually stays in the plane. It has more chance of staying in that vertical plane.
Okay. So here's a question that, because we've been looking at something similar, and the first question I always wonder is how repeatable is the system, in a sense that if you can hold as many things as constant as possible, how repeatable would be the output? So in your case, because you're varying the launch and the objects and the targets, but if you do the same exact launch and the same exact response, how consistent is the response there?
That's a great question. I think, yeah. So if it stays in the vertical plane, and I think our modeling of the flight is pretty good, as I showed you, and I think it could be very repeatable. A lot of the failures we have is because the dumbbell thing with the dumbbells and with the ball, we didn't have that much problem. With the dumbbell, it actually goes out of the plane. Oh, yeah. It's not actually moving in the plane. So that causes the problem. But for the motion side, I think the robot has a very good estimate of the velocity, angular velocity, and the orientation. And there is a little bit of a cushion for the batting as well, because for the impact modeling, and there are some errors, but the errors are not to the degree of affecting the outcome. It's mostly that the motion deviating from the vertical plane that caused the problem as we observed.
Okay, good. So maybe others can jump in with questions. I have to run in a minute, but I do have one more if there isn't another question. Okay, I'll ask so the other question is to do with the cutting, because I find it very interesting that you really build these beautiful physics models of the scenario, and cutting an onion is one of the most challenging things I find. In particular, especially there's sort of a sweet spot where you can cut it, and then it gets very hard at a certain point when it's toward the end. Especially, my wife likes onions very thin, so I'm trying to always cut them, really just cut them like that. And then as I get toward the end, it gets very hard to do that because it's actually the structure of the onion starts to fall apart. So the onion, as you're down toward the end, it tends to, I don't know how to describe it, but it's sort of the layers start to open up and it starts to slip. Yeah. So there's a real interesting question of fixturing there. How do you fixture? Because your hand isn't quite the right tool for that. And
right.
I'm just wondering, because the other thing is if you put pressure on both sides, it seems like that could work. Yeah. But then that would probably give you a much different dynamics.
Yeah, that's a great question, Ken. I think we've also thought about that too. If you use a fixture though, and then you will not be able to cut the entire onion. And onions have different layers, which tells you that the fracture toughness changes every small movement, downward element movement, because it goes to the separation layer, and then has a tougher skin there in between. And now the question is, if you have a holding hand, imagine you have an anthropomorphic hand that actually holds the onion and using finger gates, to move on the onion, and so to leave the space for cutting. That'll be great, I think, if anything can be done in that,
I think that's an interesting challenge, is to, even with a simple parallel jaw gripper, some kind of gripper, to think about how it would adjust and adapt during the
Mhm.
process. It'd be very interesting now that you're cutting, um, to put those two things together. And because there's essentially a grasping problem, which
Right.
prevents the cutting.
And then
And
there's also the moving, because you know, like human cutting, we grasp the onion and we push forward, sliding it on the cutting board, right, forward. So they coordinate.
absolutely. And actually, for many things, like I think about green peppers or something like that, where you actually you hold it in a certain way that you press it so it gets stiff, and that
Hmm.
helps you cut.
Oh yeah, yeah.
There's some nuances there with maybe more deformable vegetables, that
Right, right.
like if you're cutting, let's say, a head of lettuce or something, you have to
Hmm.
make it a different way. But a really nice problems, and it's certainly, as you said, this is relevant for surgery because I think this is one of the big questions, unanswered questions in robot assisted surgery, is really trying to model the responsive tissue. And there you have very, tissue are very highly deformable.
Right, right. So there's viscous forces there as well that need to be somehow modeled. And actually, the thing about modeling is that you don't need a very accurate modeling because the control has some tolerance, can make up for some errors. If you set the gains, you don't
Well,
need exact.
well,
Um,
it's interesting because humans are very good at it. We know this, and that's a beautiful,
right.
existence proof that surgeons do this all the time. They can do incredible maneuvers in with teleoperation, but it's so far in terms of autonomous has really been elusive.
Yeah,
And
yeah.
so, we're working on suturing, but just trying to do some just reliable cutting is very, very hard. So I
Maybe
think,
some of this data-driven approach, like people are already working on that, could help to some degree. But eventually, I think that's contact-based tasks. It has um, to use control to make it compliant, and
I
and
agree.
smooth. Yeah.
Yeah. All right. Well, Yanman, thank you so much for a great talk today. Super
My pleasure.
creative, and I wish you really all the best. And
Thanks,
so glad to
Ken.
have you here.
Thanks to
Um,
everyone for attending. It's my pleasure.
all right. Thank you so much, Yanman. We'll be in
Thanks.
touch. Okay.
Yeah, thanks.
Thank
Bye-bye.
you. Bye.
Bye-bye.